We started looking at 3-stage op-amps yesterday. So we actually did very little, right? We just replaced the second ideal op-amp with a 2-stage op-amp. But let's start first looking before we go there. We're going to go back there. Before we do that, let us say I had 3 stages. So let's say this was my op-amp. And each one had a gain A, and each of these was single pole. Okay? And this is VO, Vn. If I draw the Bode plot of the gain in dB, what will it look like? So what is the gain going to be at low frequencies? Yeah, so I'll call it A0 cube, right? I'll assume that each one of those things is single pole, A0 over 1 plus S over omega P, okay? And then after that what happens? It will go at 60 dB per decade. And we also know that if each single pole has a bandwidth omega P, the overall 3 dB bandwidth of the cascade is going to be lesser. We also saw several classes ago, right at the beginning of the semester, right? We saw how much it reduces by. So we also know it is going to reduce the bandwidth. What can you tell about the stability of the system if you place it in feedback? Let us say you have 3 gain stages which look like this. You place this in feedback. What is going to happen? Is it going to be stable or unstable? First of all. Unstable. Why? Yeah, so you want it to pass at minus 20 dB per decade. We already saw that, right? If you have a single pole system, it's definitely stable. You'll have a very large phase margin as long as the second pole is very far away. And we also found conditions. If the second pole is right at the omega u, phase margin is 45 degrees. Since you have 3 poles right here, you can say pretty surely the system is going to be unstable in feedback. Okay, so this is not going to work out. Okay, so then what will you do? If you had to rearrange things, what would you do? Knowing what you know about, op-amps, gains, poles. No, so you have 3 stages, right? How would you apportion the gains? So right now I have assumed equal gains and equal poles. If you didn't have that restriction, what would you do? Yes? Dominant pole. Okay. So what do you mean by dominant pole? What will you do? So I have 3 things. A1 over 1 plus S over omega P1, A2 over 1 plus S over omega P2, and A3 over 1 plus S over omega P3. How would you place the relative poles omega P1, P2, P3? Make one pole very less, make the other poles very large. Okay, so that is one thing you can do. What about the gains? Can you make the DC gain the same? First of all, is that optimal? What do you know about the gain and bandwidth trade-off? We know that low gain stages have fairly wide bandwidths and vice versa. If you try to make very large DC gains, usually the bandwidth is very small, right? So if you really want to apportion the, you do this for the first stage, maybe do this for the second stage, maybe do this for the third stage. You do something like this, right? Where you would make the gains different and the bandwidth different. What will the overall bandwidth look like? So let us say this was a dominant pole. Oops, sorry. In this particular case it comes here. I'll get a second pole here. And then somewhere here I'll get a third pole. It should go down. Right? Is this stable or not? As I've drawn it? It's stable. And it's probably going to have phase margin slightly larger than 45 degrees. I can also say that. Right? So typically, if you see this is the you could say the three-stage architecture we started off with yesterday. So what can you say about the gains and phases? At least definitely the pole positions, not the phases, sorry. The pole positions. You would definitely expect, so first of all, you're starting off with 3 stages. Let's say you're not added the compensation yet. Starting off with 3 stages. Okay? You would probably, what you would want is, the overall 3-stage op-amp has a pole that corresponds to a unity gain frequency of GM1 over SC. Right? So you would expect that the pole of the first stage, which comes here, to be the largest. Then next would be the pole here, and finally the pole here. Correct? So this is exactly what we started off with, right? If that's what you want. If you see from a high level perspective, that's what it seems like, that's what you want. Correct? From a 3-stage op-amp. Is that right? Okay. So let us go back to our, I'm going to copy this guy. Okay, so we want, I'll call this GM1, GM2, GM3. What is omega U? We just said it, I mean, it's GM1 over SC. Sorry, why do I keep saying that? GM1 over C, right? Omega U is GM1 over C. This is C, this is C prime. Okay? What is the DC gain? Right? This is the DC gain. What is the dominant pole? I'll call this A0. What is the dominant pole? What is this? If you have a single pole system with a unity gain frequency of omega U and a DC gain A0, what is the dominant pole? Right? Correct? Okay? So what we'll do is, so let us say this whole portion has some gain A. We'll start off with A. Maybe I should use a different, what shall I call it? Maybe A2. I'll just call it A2. Okay? Let's call this A2, this is C. Okay? I'm going to call this A2 of S in fact, because you know it does depend on frequency. Okay? So how would you analyze the system? Let us say you have to write the overall transfer function approximately in terms of A of S, GM1 and so on. What is the current drawn here? GM1 over GM1 times VD. Okay. What is the voltage here? Yeah, what is it? Should just be VO over A of S. Is that right? You have the amplifier. It has a gain A of S. Output voltage is VO. Input voltage has to be VO over S. Is that right? What is the current through the capacitor? Okay, but you can also write it in terms of VO, right? Okay. Oops, sorry. SC times VO minus by A of S. Okay? If I had to draw the signs of the op-amp, what will it look like? It will be minus plus. Right? So, this voltage will actually be minus VO over A of S. Correct? It's connected to the negative output. Is that right? So you just have to equate these two guys. Okay? What is, sorry. Yes. Current drawn? Sorry, I'm not able to hear you. Current drawn through G? Okay, right now we are going to neglect that because we are trying to do a very high level analysis. You are right. So in fact, this analysis is very approximate, and you'll see because in reality the analysis of this system would be more complex. Okay, since we are doing it in class, right now we'll neglect the output impedances of the op-amps for this analysis. Okay, if you really do it, yes, it will be slightly different. And similarly, there will be some zeros and so on. We are actually neglecting a bunch of these things. We are going to assume that the op-amp is an almost ideal voltage control voltage source. Okay? What is it? Is that right? Is that right? A by 1 plus A. Okay. So, what do you, oh, sorry, I should be careful. A2 of S, A2 of S. Okay. Okay. So, what is A2 of S over 1 plus A2 of S going to look like? First of all, what is A2 of S? That is the gain of the two-stage op-amp, which you are going to replace the ideal op-amp with. Okay? And that you already know what that's going to look like. Sorry. You ideally want it to look something like this. Correct? Is that right? I'll call this omega u inner. What is that? This is just GM2 over, actually in this case GM3, right? What did I call it? Oh, GM2. Okay, just wanted to make sure I've got the things right. Okay, so it's GM2 over C prime, correct? And you are going to get an extra pole also, some I'll call it P2 inner, which is going to be far out. Okay, so what is A? This is A2 of S, A2, okay, the magnitude. What is A over 1 plus A going to look like? At very low frequencies. At very low frequencies, what is it? It's flat. It's going to be 0 dB. At very high frequencies, what is it? It's going to follow mod A. Okay, so we'll just make an approximation that all the way down here it's like this. We'll just make an approximation. In reality, it's true only in this region and this region, but we'll assume this is another approximation just to see what happens at from a very high level perspective. Okay. So now, where is my overall? Okay. So now, what can you say about the overall transfer function? What is this going to look like? So you have found out what A over 1 plus A looks like. That multiplied by GM1 over SC is going to give you the overall transfer function. Correct? So this is GM1 over SC, okay? GM1 over C. Now once you multiply it with this guy, what is going to happen? So you already have that condition, okay? Greater than, I'll just call it omega u, right? That we already know, correct? And in fact, I've drawn it a little bit wrong. At omega u, when does the first pole strike? So left by itself, GM1 over SC would just go as a straight line. But now you are multiplying it by A over 1 plus A. Where does it have a pole? At omega u inner. You'd have a second pole here and a third pole here. Correct? And of course you also have this condition. Okay? So it looks like you have a system with one dominant pole because of C, and then the first non-dominant pole is because of C prime. The second non-dominant pole is because of the P2 of the inner loop. And of course right now we have not considered zeros, we have not considered there will be other poles also. Okay, there will be a P2 for the outer loop also. Right, we are not even looking at all of those. Okay, so but fundamentally you are getting poles at A over 1 plus A. The poles of A over 1 plus A are appearing in the output. Those are the extra poles. So what does this tell you about the 3-stage op-amp? Fundamentally the speed is, it is going to be slower. The omega u definitely has to be smaller than what you can achieve with a 2-stage op-amp. Right? Because the second stage, at least in this configuration, we'll see if there are other configurations. In this configuration at least, the omega u of the 3-stage op amp is definitely going to be smaller than what you can achieve with a 2-stage op amp. Okay? So what are the conditions? Sorry. Omega u inner. This is GM2 over C prime. P2 inner. What was P2 inner? It looks something like this. If you remember, GM2 over C prime over C plus C prime over something like this. Okay? You can go back to your 2-stage op amp, find out what the first non-dominant pole was. It looks something like this. Okay? But the advantage is your DC gain is very large, so your steady state error will be very small. Okay? So this just tells you the general trend. It doesn't tell you, details. You have to remember that. Right? Tells you the DC gain, tells you the, omega u is lesser and so on. But if you really get down to designing this 3-stage op amp, things will be quite complex. So we probably won't deal with the design of 3-stage op amps in this course. This is just to tell you that there are these kind of structures. So this particular structure is called a nested Miller. Okay, so you basically have one Miller loop nested inside a second Miller loop. Okay, that's why it's called the nested Miller. And let's say this has a pole P1 and a pole P2 and a pole P3. Okay, and of course, so you have capacitances C1, C3, GM3. Okay, so let us say you actually start off with none of these guys, right? You have designed each stage separately. Now you want to add the compensation capacitance. First of all, what's going to happen? We first need to compensate the inner loop. So what we'll do is we'll add C prime. What is going to happen to the pole position? So let's say you had P2 and P3. Right now this is just the inner loop. So P1 doesn't come in. You have P2 and P3. What happens when you add C prime? So you're going to get P2 prime here. Right? This is going to move out. You're going to get P3 prime. Correct? You're going to get the usual pole splitting. You're going to split the poles. P2 is going to move in, P3 is going to move out. That's what we know. That's your P2 is the value, is the point where you get the Miller capacitance. Correct? Okay. So what happens now if you add overall C? I'll just add it here. What happens when you add C? What is going to happen? P3 and P2 are? P3 and P2 will move left. No, P2, now you have P2 prime and P3 prime. You no longer have P2 and P3. What is going to happen to P2 prime? It will move left. Why will it move left? Actually, why will it move left? Huh? It doesn't? It doesn't change at all? So it so happens, okay, so let's start off at P2 prime. It will move even closer. Okay, the analysis, you can analyze it and see it. I'll just give you the results. Turns out P2 prime will move even closer. What do you have here? You have P3 prime. What happens to that? Turns out it's going to move out. You're going to split again. Okay? But now you have one more thing thrown into the mix. You have P1. What happens to P1? P1 is going to move in. That is your Miller. Okay? Is that right? So what happens? So let's say you add the Miller capacitance C and you keep increasing the value. So the poles move. What happens? So P3 prime moves left, P1 moves right. What's going to happen? Will they cross over? What usually happens when you have two poles move? You must have studied this in the, I guess, control system. Some of you must be getting to the close, right? So you must have seen something like this. What happens when you have two poles moving, towards each other? Exactly. So at one point they'll coincide. After that they'll break into a pair of complex poles. Okay. So you'll get something like this. Okay. So if you look at the way the poles move in this nested Miller, they'll look like this. So you'll have a pair of complex poles and one dominant pole. Okay. So it turns out, okay, so I'll leave the other stuff behind, but you can find out the omega u. The analytical design is quite difficult, so I won't do it in class. But you can do everything and show that the final omega u you get will be, this is J1 over C, of course, but this turns out to be approximately 1 over 4 P3 prime. In the two-stage op-amp, you got something like this. Okay, you get something like half. So the bandwidth of this is definitely lesser by at least 50%. So there are other structures which have been designed to improve the bandwidth further. Okay, so this one has a fundamental problem, right? So there is something called a multipath nested Miller configuration. So you have P1 here, P2 here, and P3 here. Oh, yeah. Okay. You have P1, P2, and P3 here. Okay. Now what you're going to do is, you're going to add a feed-forward path. From the input to the output of the second stage. Right? Fundamentally, your bandwidth is falling off at higher frequencies. Okay? So you're going to add a feed-forward path. I'll call it GMF, and of course, you're going to have some pole here associated with that. What is this going to do? If you add a feed-forward path like this, it's going to add a 0. Okay? So now what you can do is, you can use this 0 to actually cancel one of the poles and improve the bandwidth. Okay? So in other words, at low frequencies, you get most of the gain from GM1, GM2, GM3 path. At high frequencies, the gain of the GM1 path falls off because you have the pole at, right, through the main path, but you are going to try to supplement it with extra gain through the GMF path, in other words. That's typically what you do with a 0. Okay? And now you can get conditions. I'll let it go, but you can get conditions on, for this pole 0 cancellation and so on. I have some basic details in the notes. You can just go through it. Okay? It's not relevant for this class. And okay, so this, you have multipath nested Miller. So similarly, for example, you can actually do this too. Instead of doing GMF across the first two, you can do it across the second and third stages. Okay? So what is the difference between these two? GMF and GMF prime. So fundamentally, when you add GMF, you are adding extra noise and offset at the input. Right? You are connecting the new amplifier directly at the input. So any noise which it produces will appear directly, add directly at the input. Any offset will directly add at the input. Okay? Whereas if you when you add GMF prime, it gets divided down by the gain of the first stage. So that's not a problem. Okay? What else? Is there anything else? You probably have some load capacitance there. Now GMF has to drive that load capacitance. Right? So it's quite possible that you might need to burn extra power in GMF prime than in GMF. You might need to worry about slew rate, other concerns. Yes. Well, what is it? I mean, if you just add across one opamp, it's just the same thing as increasing GM1, right? That doesn't help you at all. That is part of the original trade-offs. If you just add a GM across the first opamp, that doesn't do anything for you. Right? Actually, right now we are assuming that GM by itself does not have any poles at all. Why, right? We have not even looked at, the differential pair has its own mirror pole. We never considered all that. We are just assuming at this output point, at all the output points, you have a pole. Right? So if you add anything across just the first stage alone, it's just in increasing the GM, nothing else. Now you can think of, so that's the trade-off here. Now you can also think of combining the two. So now you can add nested Miller along with feed-forward stages. You can make multi-stage op-amps, not just stop with 3. You can keep increasing it. There are lots of papers. Okay, if you want references, I can give you, if anybody is really interested. Okay. Okay, so we are pretty much done with op-amps. Okay, so we'll move on to we'll start off with bandgap references, maybe 2-3 classes, and then we'll start off with output stages. Okay. Okay. So I guess, has anybody heard of bandgap references before? Well, apart from last class, before last class. Nobody's heard of bandgap references. Okay. So the main idea is you want a reference, a voltage or a reference current which is independent of process voltage temperature. Okay, that is the basic idea. So most of the current sources we have seen, right, depend in some way or the other on the process or temperature or voltage. For example, we always assume there is one, ideal current source available to us. What is the ideal current source? Right? We assume that it doesn't depend on the supply voltage. Of course, you can take a current mirror, add a resistor to supply on the left side. That will give you a current. VDD minus VGS over R will give you the current. But of course, if you change temperature, VGS is going to change, R is going to change, your current is going to change. If you change supply voltage, it's going to change. Right? So definitely that is not going to work. Anything depending on an IC resistor is not going to work out. Okay. So let us say you're trying to create this bandgap voltage, and you'll soon see why I'm calling it a bandgap voltage. But let's say you're trying to create a temperature independent voltage. So you can think of it as being generated through a linear combination of two voltages. Okay. Now what is the condition? Your condition is that dou V by dou T is 0. So first of all, we start off with temperature independence. Okay. Of course, if you make sure it's temperature independent, it so happens in IC processes, almost all parameters change with temperature. Right. All the process parameters. So if you want to make it temperature independent, it almost surely means that you have to make it process independent also. Right, because if it depends on any process parameter, when you change temperature, the process parameter will change, your voltage will change, reference will change. Okay. So what does this mean? So I have alpha 1 dou V1 by dou T plus alpha 2 dou V2 by dou T is 0. Right? In other words, I need to create two voltages. One of them needs to have a positive temperature coefficient. The other needs to have a negative temperature coefficient. So that when I take a linear combination of that, it is insensitive to temperature. Sorry? Of course, alpha 1, alpha 2 has to be independent of temperature. Right? Okay? But you do know how to create temperature independent. Right? What do you try to do if you need to create something which is independent of temperature, gain, let's say? What do you do? Independent of temperature, process, and so on. Ratio of resistors is an example, right? If one resistor increases by a certain percentage, you make the other resistor the same type of resistor, the temperature coefficient is the same, so therefore the ratio of resistances will not change over temperature. Similarly over process. Okay? So it turns out that the base emitter voltage. So first of all, the bipolar characteristics are very well known. You know, they are fairly well studied, and it turns out it actually gives you a very reliable temperature dependent voltage, which happens to be the VBE of the bipolar. Okay. What is VBE? If you have to write it in terms of other parameters. Okay. VT ln IC by IS. Okay. Suppose you had to find out, first of all, suppose you had to find out dou VBE by dou T. What is that? What is VT? KT by Q. So that is the temperature dependence. What else? IS is temperature dependent, right? So we need to find IC. Of course, you can make sure it's not. Okay, but we'll see. Okay, so let's assume IS is temperature dependent. So this is the dependence of IS. The saturation current itself is proportional to mu, KT and Ni squared. What is mu? The mobility. Mobility of the minority carrier. Similarly, Ni is the intrinsic minority carrier concentration of silicon. Yes. We'll come to that. Okay, we'll come to that. We'll see there are ways how you can. It doesn't have to directly depend on IC. You'll see, right? Right now we'll just do it this way. Does mu depend on temperature? It does. Oops, sorry. So there is some dependence on temperature, some T power m. Yes, you have a question? Okay. It's somewhere around -3 by 2. Okay, approximately. Ni squared is proportional to T cubed times minus Eg by KT, where Eg is the band gap of silicon. Okay. Something like 1.12 electron volts. This is the band gap energy of silicon. Okay. So now you get rid of all the proportionality constants. You'll just make it some B times what will you have? T power 4 plus m. Correct? You get a T cube from here. You get an m T power m from here, and you get an extra T. Correct? Yeah, of course, I'm writing that. Yeah. Okay? E power minus Eg by KT. Okay? Sorry. Everybody got that? Noted that down? Minus Eg by KT also has a temperature. Of course, Eg is constant, but the KT has a temperature dependence. What is dou VB by dou T? Dou VB by, dou VB by dou T. Correct? I just differentiated the two parts separately. Huh? Yeah, so right now we'll come back to that. Okay, right now just assume that IC does not have a temperature coefficient. We'll come back to that. Okay? Okay, so what is this? Oops. So now that will have two parts, right? You'll have B times T power 3 plus M times e power minus Eg by kT plus B times T power 4 plus M times e power minus Eg by kT times Eg by kT squared, right? Okay, so this just happens to be 4 plus M by T plus Eg by kT squared times Is. Right? Okay, actually let's stop here.